If you recollect, I have introduced to you the concept of modulation, amplitude modulation yesterday, and we were in the process of discussing one kind of amplitude modulation which is called double sideband with suppressed carrier amplitude modulation. Right? We had looked at the waveform, we had looked at the spectrum, and we were looking at the demodulation for such a signal. Right? How do we get the message signal back from the modulated signal? Right? And we had agreed that the demodulation process would be very similar to the modulation process. Right? The received signal x of t, which is equal to a times mt times cosine omega ct, once again needs to be translated back. We have to go through a translation, frequency translation process, so that we get a component around the zero frequency, that is a baseband component. Of course, in the process we will get a component around 2fc as well. Right? And therefore, the demodulator will have the same multiplier that we had at the transmitter, which will multiply the received signal with the carrier 2 cosine omega ct and followed by a low pass filter. Right? And hopefully this should be a replica of the message signal mt, maybe with a scaling constant, etc. Right? Mathematically speaking, you are multiplying xt with, so let's say that the output here, let's call this signal z of t, right? So z of t is some constant k that will be associated with this multiplication process of mt into cosine omega ct into 2 cosine omega ct. Right? This is what you are doing mathematically. In multiplying the received signal with 2 cosine omega ct, I have just introduced a constant k which may be associated with the multiplier. It may not be, it may be producing an output proportional to the product rather than equal to the product. Right? That's acceptable to us. So this will be equal to, as you can see, when you get 2 cosine square omega ct, which you can write as 1 plus cos 2 omega ct. So this will be k times mt, the first part, plus k times mt cosine 2 omega ct. I have skipped one step in the process. Okay? And in the frequency domain, this would appear to be, if I take the Fourier transform of this signal, this will be, the first part will have a Fourier transform which is k times the desired spectrum m of f, plus you have components at the translated version of mf around 2fc and around minus 2fc. Right? This is, I hope, understood. I am just writing the Fourier transform of this. This part is k times mf. The Fourier transform of this part is mf minus 2fc plus mf plus 2fc. Right? And as we know, if we can ensure, if we know that our fc is suitably chosen, right, so that, what is the requirement? That the bandwidth b of let's say bandwidth of mf are the largest largest frequency component in MT, right? If this condition is, if this satisfies the condition that B is less than FC, then obviously it will be also less than 2FC, and these two spectra would not overlap, right? So these are non-overlapping spectra. This portion of the spectrum is in a much higher frequency band, well removed from the spectral domain, spectral support of M of F, right? And therefore it will be very easy to separate this out by just putting a low pass filter, right? So this low pass filter should have a bandwidth of how much? The desired signal has a bandwidth of B. That's what you want. You only want the desired signal to appear in the output. So this low pass filter should have a bandwidth of B, right? And naturally then the component which are centered around 2FC would be eliminated, right? So in the frequency domain what we have is the Z of F will look something like that. There is a desired component from minus B to plus B, and this part is around 2FC, same thing, and this part is around minus 2FC, same thing. And if you make sure that your low pass filter,
so this amplitude is double of,
yes, okay, this amplitude is K and this is K by 2, which is not reflected in this diagram. You can correct it suitably. So if you have a low pass filter with a response like this, let us say, obviously this signal will get eliminated, and what you will get at the output is the product of this frequency response with this input spectrum, and therefore you will just get your M of F back, right? Is it clear? So that's the low pass filter transfer function. So that's a demodulation. Looks simple enough. There is a small complication which you should be aware of. The demodulator, if you look at it, requires a local carrier, right? At the receiver, I must have a replica of the carrier that was used at the transmitter. Now that doesn't appear to be a big deal, but you must remember that there is a requirement here. This local carrier must be precisely at the same frequency as the one that you have used at the transmitter. It should have precisely the same phase as the phase of the incoming signal, carrying the incoming signal. Because if these two conditions are violated, you will not get a perfect demodulation of the kind that we have proved mathematically to be so. The input was being, your modulation was being done by multiplying MT with A cosine omega Ct, and we are assuming that a perfect knowledge of frequency and phase of this signal is available at the receiver, right? So that you can multiply it by a local carrier, a replica, and get your demodulated output. So implicit in this demodulation process is the concept of synchronicity between the transmitter carrier and the received carrier, and the local carrier of the receiver, right? So therefore this is also called synchronous demodulation. Yes, please.
So you are saying that it should be exactly the same frequency.
Yes.
Somebody takes another frequency.
We look at that now. We just see what will happen if the local carrier has a frequency which is slightly different from the actual value of the carrier frequency. We will see what is the effect. It will make a difference. We will see that in a few minutes. In fact, that's the next thing we will do. So this kind of demodulation is called synchronous demodulation, whereby we imply that the demodulating signal or the local carrier at the receiver should be in perfect phase and frequency synchronism with the carrier of the received signal, right? Because if it is not so, we will not get a perfect demodulation. Let's see why, right? So let's look at the effect of loss of synchronization, right? If your synchronization is not perfect, what will happen? We also call it effect of loss of coherence. We are saying that the local carrier and the incoming carrier are coherent with respect to each other. By coherence, we mean essentially it's a term for indicating that they have the same frequency and they have the same phase, right? That's what we mean by coherent here. So if there is a loss of coherent, occurrence, then there will be some undesirable phenomena taking place. Okay. Suppose your local carrier is of the kind 2 cosine omega c plus delta omega t plus theta, right? Your incoming carrier is omega ct, but your local carrier has a slight frequency perturbation, right? It's not exactly omega c, but omega c plus a perturbation delta omega, right? And also there is a phase difference theta. Okay, so if you go through the same trigonometric equations once again, it's very easy to check up just through trigonometric identities. Then the recovered signal y of t is now given by not k times mt, which was the case earlier, but can you guess what it will be? It will be k times mt into cosine of delta omega t plus theta. It's very easy to check this out. Right? Multiply the two, apply the trigonometric identities of cos A into cos B, and look at the term which is the low pass term. Right? So we will get this output rather than k times mt. To appreciate what this output is like, let's simplify the discussion first. Assume that there is no frequency perturbation, that the frequency at least is perfectly synchronized. So let's say delta omega is 0, right? Case 1 where delta omega is 0. Now what will happen? So y of t would be k times cosine theta, k times mt into cosine theta. Seems alright, isn't it? Because cosine theta is also a constant. But see what will happen if theta is pi by 2. You lose a signal, right? Right? So if theta is pi by 2, y of t is identically 0. So basically cosine theta now becomes an attenuation factor, right? The recovered signal is of course just a scale. There is no distortion in the recovered signal. The recovered signal is still proportional to mt, but the problem may be that you don't have a recovered signal at all, particularly if your phase difference is as much as pi by 2, right? So you can see there is a perfect phase matching required, phase synchronization required. Is that clear? Now let's look at the case where theta is 0, just to simplify the discussion again. Of course this doesn't really simplify too much. Theta is 0, but delta omega is not 0, right? So y of t now is equal to k times mt into cosine delta omega t, and now you can see that there is a distortion as well, because you are getting a function of time which is not the same function of time that you want. It is being multiplied with another function of time. It is the product of two time functions, the one that you want and some additional time function which is coming in the process.
But then you have to take the Fourier transform also, right? When you take the Fourier transform,
just a second. What Fourier transform? You are looking at the recovered signal y of t. Fourier transform only will tell you what is happening in the frequency domain, but this is what you are getting. Is that okay? After multiplying and low pass filtering, this is the output that you are getting, whereas what you wanted was k times mt. So instead of getting what you want, you get that into something.
If you pass it again to another low pass filter, this time I will be getting mt.
Delta omega is okay. His doubt is if you pass this through another low pass filter, you will get mt back. Please remember that this is a modulated signal again, but the modulating frequency is extremely small. Even if it has a high frequency, a low pass filter would not be able to remove it, because the whole thing is translating around that new frequency, right? So in fact the low pass in that case the low pass filter would remove everything, right? But the important case to discuss here is not that case, but the case when delta omega is very small, because that is what will practically happen. You will have a local carrier, you will try to adjust its frequency to be as close to that of the incoming carrier, but maybe there is a very small frequency difference left and you are not able to take care of that, right. So this may be of the order of a few hertz, maybe tens of hertz or at the most hundreds of hertz, right. Typically tens of hertz. If you are using very stable oscillators both at the transmitter as well as at the receiver, the typical frequency difference will not be that high, right, which will be the case in practice. And in that case, basically what you see is that cosine delta omega t will be a slowly varying sine wave multiplying your empty, right. This delta omega is very low frequency here, so delta omega is typically small, right. So what will you see? You will see that your incoming signal is multiplied by a scaling factor, which is sometimes going up and sometimes reducing significantly, right. So the amplitude will go up and then will come down and will then go up and so on and so forth, right. And you will therefore see you will hear a distorted version of the actual signal, and the kind of distortion that results is called wobbling distortion. This is kind of wobbling phenomena, right, amplitude going up and down. This is called wobbling effect.
So the recovered signal which I got is basically around the frequency, not around the carrier frequency. I have nothing to do with the carrier frequency.
The carrier frequency is out.
So it will be around 0.
That's right, it is still around 0. But effectively what is happening is, in the frequency domain, if this was your original spectrum, right, it is getting slightly shifted. So you will have a portion like this and a portion like this, right. It's the sum of these two spectra that you will get, right. So there is a slight frequency shift to the left as well as to the right, and what you will see is the resultant of these two. It's no longer the original spectrum. The original spectrum is this dotted line, right. That is what is happening in the frequency domain. Is that clear to everyone? So this therefore is called the wobbling effect. Now that therefore underlies the importance of what we call carrier recovery in this kind of a demodulation, right. You require a fairly sophisticated, a fairly good carrier recovery system, right, by which we will be able to establish a local carrier which is in perfect phase and frequency synchronism with the incoming carrier, right, and that operation is called recovering the carrier, right, at the receiver. So a carrier recovery circuit is needed at the receiver. And what will the carrier recovery circuit do? So produce a synchronous carrier, produce a coherent carrier, coherent local carrier, right? And this kind of a thing can be done by using a device called the phase lock loop, etc., which we shall discuss when a little later, right? So there are special circuits one has to make to carry out this carrier recovery operation, to make sure that your local carrier is in phase and frequency synchronism with the incoming carrier. And that's why a synchronous demodulator is typically a complex operation, because you need to worry about this, right? You need to worry about carrier synchronization. Okay. Any questions at this stage?
So why can't we transmit the carrier just as if, apart from the carrier which is carrying?
That's precisely what we are going to do next. So as you can see, one of the disadvantages of double sideband suppressed carrier modulation is the need to carry out synchronous demodulation, which has this complication, right? So as has just been suggested, we should explore the possibility of a scheme in which we actually transmit the carrier also, right? And see whether that helps us simplifying the receiver, right? And that's precisely the thing that we're going to discuss next, and that is double sideband AM with carrier rather than without carrier. So this is no longer suppressed carrier, we also put a carrier component in this. So basically what we are saying is, in fact, when generally one refers to amplitude modulation in practice, one is typically referring to this situation and not the suppressed carrier situation that we have discussed so far. Okay, the suppressed carrier situation is used typically, or was used earlier in the earlier days, typically for transmitting data signals. For voice signals, this is one of the most commonly used form of amplitude modulation, right? So basically what we are saying is that in this case your transmitted signal x of t would of course contain the part that we were transmitting earlier, but we also put in a carrier component. So it looks something like this, right? As you can see, the second term is precisely the same term that we had earlier, right? A times mt times cosine omega ct, but we are also adding a term which is equal to a cosine omega ct, right, which is a carrier term. So there is a carrier component specifically introduced along with the message signal, along with the rest of the modulated signal to produce the final modulated signal x of t, right? And let's define this as some e of t into cosine omega ct, where e of t is defined as a times 1 plus mt. Now this waveform, let's look at the time domain behavior of this waveform, can be made to have some can be made to have a very interesting property under a certain condition. For example, if I ensure that if the magnitude of the modulated if the magnitude of the message waveform in this equation is always less than 1, right? Think of this as 1 volt and mt lying between minus 1 volt and plus 1 volt. So that I can basically what I am doing is scaling the message waveform in such a manner that its instantaneous amplitude never exceeds 1. It always lies between minus 1 and plus 1. Every message will have some limits in which it lies, right? Every waveform will have some limits in which it lies. I can scale it up or down so that this condition is satisfied, right? In this case, a very interesting property that this waveform will have is that this entity e of t, which you can now consider, you see this will be a positive quantity always, 1 plus mt will always be a positive quantity. You can think of this as the envelope of the waveform. Envelope always is positive, right? So as you can see, e of t then will have the shape of mt, right? So e of t follows the shape of mt. Of course, there is a constant 1 along with that, but that constant 1 can be always taken care of. Follows the shape of mt.
So, but wasn't that always the case?
No. In the DSP-SE case, the envelope is proportional to the modulus of mt. What we would like to have is the envelope be proportional to mt itself. And of course, why we would like to have is another issue, which I will come to in a few minutes. Right? How does it help us is something that we have to still discuss, but I just want to point out this interesting fact which was not available to us in the suppressed carrier modulation, because there the envelope was proportional to modulus of mt. Here we are making the envelope proportional to mt, right? Of course, the spectrum, so that's as far as the waveform goes. Let's maybe plot the waveform. So what we are saying is, if your message signal is a low frequency sine wave for the sake of illustration like this, your modulated waveform will now look something like that. The instantaneous amplitude of the carrier follows right. This is the envelope E of t. this amplitude is 1 plus mt, right? And if mod of mt is less than 1, you will see that this will never cross this x-axis, the time axis, right? It will always remain proportional. If it crosses the time axis, we will have a problem, because then we will lose the proportionality of the envelope that we are looking for with respect to mt. So that's why this condition is required, that mod of mt should be less than 1, right? So that's the typical time domain waveform of amplitude modulation with carrier, okay, as against the waveform that we saw yesterday for amplitude modulation with suppressed carrier, without carrier. Now before we come to how it helps us, how this property helps us, let's also look at the frequency domain. And to do that, just to for convenience, I am taking a message waveform spectrum to be something like this here. It has absolutely no reason for this particular choice. We have no particular reason for this choice, but since I want to show the carrier component a little more clearly, I have deliberately chosen the message waveform as if it does not have any component at z. But there is no requirement of this kind again, right? So suppose your message waveform has a spectrum between minus b to plus b, as a Fourier transform which is non-zero over this range. Then your modulated spectrum x of f, the spectrum of the modulated signal in this case would be like this, where this is around fc and this is around minus fc, right? The same spectrum translated to plus fc and minus fc, and in addition there is a carrier component which was not there in the suppressed carrier modulation. So the only way the spectrum of the AM signal differs from the spectrum of the AM signal with suppressed carrier is that this carrier component is not present. I hope that also answers a question as to why do we call the earlier kind of signal as DSB-SC, right? It is basically this difference. In this case we have a localized specific value of the carrier component along with the modulated signal, right? So the spectral properties of this signal are to some extent similar to that of the DSB-SC, and in the sense that the bandwidth required is 2B as against the message bandwidth of B. But so that's the bandwidth requirement. But as you can notice, there is a kind of we have introduced actually a kind of inefficiency here. What kind of inefficiency we have introduced? We have introduced a kind of power inefficiency. Not all the transmitted power contains useful information. The carrier does not contain message information, right? It is helpful to us in some other way at the receiver, right, which we have to still see, but by itself, in as far as our objective is to transmit information, that purpose is not being served by the transmission of the carrier component, right? So therefore, in that sense, this spectral component that we are transmitting is actually a waste of power, right, from that point of view. And therefore, there is a kind of power inefficiency that we have introduced by introducing the carrier component in the transmission process. So why should we do that?
In the previous case, when we were doing passing it to a low pass filter, we removed the frequency carrier frequency component which we had. Even there we were getting some information about the carrier frequency, but we were neglecting it. At least we were actually removing it and we were going for the message signal.
No, I think you have not understood the point. We were not getting the carrier frequency information. We didn't have a specific carrier component at FC. For example, in this particular case, the suppressed carrier spectrum would look like this, right? So we don't have a component at FC. Just because the spectral density has some value at FC doesn't mean that there is a component at FC, right? Yes, you can say that there is some energy present in the neighborhood of FC, right? But you can't say that there is a component at FC, right? There is a difference between that is the you have to have some understanding of what does a density function mean and what do impulses in the density function mean. When you have an impulse in the density function, right, that means there is a localized component at that frequency. There is some finite power or energy that we can talk about at that frequency. Otherwise, when you have a value of a density function which is not impulsive, if you were to ask the question how much power is carried at that frequency, the answer is 0, right? So therefore, you have to understand that issue. There is no carrier component in the suppressed carrier waveform. Right? There is a value of the spectrum at that frequency, surely, right? It could be 0, it could be something finite depending on the spectrum of the message waveform. But that has to do with the message waveform. It doesn't have to do with the carrier itself. Right? The process of modulation simply is shifting the spectrum from one location to another location. That's all we are doing. We are not introducing what we are now calling the carrier component. Is it clear? So let me restore these arrows if they can be seen. Okay. So there is a power inefficiency. Let's return to that point. And the power inefficiency is due to the fact that the carrier component that we have introduced does not convey useful information. When I say useful, I mean message information. We can't say that it's entirely useless, right? Because it has some function to perform. Okay. Now, how can we use it? One, sorry?
Coherent source. With the exact information that coherent source is produced.
Can you speak a bit loud?
To know exactly what is the frequency where there is no distortion.
So one suggestion that is being made is that the usefulness of this carrier would be that we would be able to recover more easily a coherent carrier as a receiver. That's what you are saying? That can be done. That is a possible way of looking at it, right? But another possible another answer is that the fact that the envelope follows the actual waveform, the desired message waveform, can be used to design a receiver, to design a demodulator which is extremely simple, which does not even require us to use a synchronous demodulation. If I don't require to use a synchronous demodulation, I don't have to carry out a carrier recovery process, right? And that will make the receiver very, very inexpensive, right? Because I don't require a phase lock loop or a complicated carrier recovery circuit to produce a local carrier which is in perfect phase and frequency synchronous of the received carrier, right? And that's the real advantage of EM with carrier, right? The demodulation can be effected extremely simply by using a very simple circuit which we call the envelope detector, right? So basically we use the fact that your envelope E of t is proportional to M of t, and that makes the recovery of MT very simple by a device which you call a diode detector. So you will soon see that it is such a simple device, has exactly 3 very cheap components in it and can effect demodulation, right? Whereas that earlier demodulator required you to have a multiplier, analog multiplier, a low pass filter. Low pass filter will be required here also, but also you require a complex carrier recovery circuit, which we didn't even show in that block diagram because that's fairly complex. But before yes please.
Sir, in this case you said the mod of MT should be less than 1
That's
in order
right.
to do this.
Right.
Now sir, there can be times when you don't know what MT is. For example, you're transmitting some data and you don't know what the peak is going to be. You can't divide it by the peak, so you don't know if it's going to be less than 1. How do you ensure that?
This can be ensured by knowing what you are saying. When you don't know, you have to know that, right? So typically by experience with the after all, your message signal is being produced by some source, and you can study a priori the properties of that source, right? You can find out what is the maximum possible voltage value that you will see at the output of this source. right? That knowledge is required if you want to ensure that. Otherwise, if occasionally such a thing happens, what you are saying, we will have occasionally that distortion coming in, which we don't want, right? To that extent, we have this problem, right? So, but that's not a very difficult issue. And in any case, you can be a little safe. You can attenuate or divide by a value which is larger than the expected value of peak. So that's a very easy thing to take care of. Okay, that's not a very big issue here. But before I go into the diode detector, which we will give you in a few minutes, it's a very simple device. Let me also define some attributes of the waveform that we have just talked about. The waveform I am referring to is this modulated waveform, right? With respect to this modulation, this waveform, you can see that depending on the relative value of mt, modulus of mt with respect to 1, you can have a situation where this envelope is fairly above the time axis, or it can even touch the time axis. For example, if the largest value of mt is equal to 1, right, then it will even, the envelope will even touch the x-axis or the time axis. The moment it becomes more than 1, the envelope will now become in that region proportional to mod of mt, right, because this portion will go up, this portion will come up, right. So that's what we don't want. So we define a parameter which is called the modulation index or depth of modulation. Right? So alternative name is depth of modulation, which indicates this fact that the waveform either touches or does not touch. Basically, what is the relative variation of the envelope from maximum to minimum values, right? So, and that's precisely the way it is defined. So, we will denote this parameter by mu, and it will be defined as follows: the maximum value of the envelope minus the minimum value of the envelope divided by the sum of the two. So, as you can see, this, the numerator is this value, right? The difference between these two values. This is the maximum value, this is the minimum value, right? So that's the numerator. That's the numerator. The denominator is, or maybe you can think of this as divided by 2. This for the sake of, and this also is divided by 2, right? So in that case, the numerator will be half of this value, which is one-sided excursion around this denominator, which will be the mean value, right? So you can think of ET, the denominator, as twice the mean value. ET max plus E min is twice the mean value. ET max minus ET min is the total excursion, right? So half the excursion divided by the mean value is the modulation index. Right? Half the peak to peak excursion divided by the mean value of the envelope gives you the modulation index, also called the depth of modulation. So clearly, if your condition mod of mt less than 1 is satisfied, what can you say about this ratio? It will always be, it will imply that mu is less than 1. Sometimes we express it in percentage, right? Particularly when we refer to depth of modulation. If it is 1, we call it 100% modulation. If it is less than 1, we just multiply it by 100. So modulation index of 0.7 would also be 70% depth of modulation, right? So typically, the value of modulation index will be less than 1, less than or equal to 1. This is the condition for distortionless envelope. Right? If you want the envelope to have to follow M of mt without distortion, this is the required condition. Okay, we already seen that the bandwidth requirement, transmission bandwidth would be 2B, right? What about the transmitted power? What will be the transmitted power? Last time we derived this to be equal to S sub C into S sub M, where S sub C is the carrier power and S sub M is the message power. So what will it be in this case? That's all. We just have to add S sub C to that value, right? Out of which is the useful power from the point of view of carrying information of interest? This part, and that also tells you the power inefficiency, right? What is the power efficiency there? So that's right. So since the carrier conveys no useful information about the message, we can define this factor power efficiency, call it E or whatever, eta or whatever notation you like to use, which is this product divided by S sub C plus S sub C into S sub A. Typically this value will be less than 50% for any message signal. It can be proved, right? I am not proving that here, but one can prove this. Yes, right? In fact, if you take your message signal to be a sinusoidal signal, like the one which we are discussing here, then one can show very precisely, and in fact I would like you to do that as an exercise, that in that case the efficiency is of the order of 33.3% with the modulation index of 1 for sinusoidal modulating signals. Right? So if your message mod, in this particular case is the one in which your MT is a low frequency sine wave, right? And modulation index is the larger the modulation index, the larger the power efficiency that you will have. So the largest power efficiency that you will get in this case is about 33%. In general, for arbitrary waveforms, it cannot be more than 50%. That can be sure, right? It has always got to be less than 50%. So therefore, there is a significant power inefficiency involved in this process, right? And one very relevant question to ask at this stage is, because we have been I have been mentioning in the past that the two most important resources in a communication system are the power that you transmit and the bandwidth, right? So here we are trying to waste power. One would not like to do such a thing unless one gets something significant out of that, right? And the significant thing that we get out of this is the fact that your receiver is extremely simple, and that kind of thing is useful if you have one odd transmitter somewhere and perhaps millions of receivers or hundreds of thousands of receivers, right? In that case, waste of power at one location is perhaps worthwhile, because so many the receiver becomes simple for so many users, making the receiver cost much lower than otherwise, right? And that's a real benefit. So the real application of this kind of thing would be where? In broadcast applications, right? When you're transmitting at one transmitting station and a large number of people are tuning into their receivers and trying to recover the demodulated signal, right? So therefore, the power inefficiency can be tolerated in broadcast applications. Due to low cost of resulting receiver. Okay.
So what is the alternative? There is no alternative.
Alternative is to go for DSPSC.
So but AC is how would you make the carrier?
Can be done. It's not undoable. All that I said is it's more complex. So if you agree to pay the cost for that complexity of the receiver, you can do it. It's not undoable. It's perfectly doable. You can have a synchronous receiver, right? The fact that I am doing this doesn't mean that we can't have a synchronous receiver. If you are ready to pay the cost for it, Let's say in some application power is a very important thing. The obvious thing to do would be to go for that rather than go for this. Right? If power efficiency is a very important requirement in an application, we would not like to go for this. We would rather pay for the complexity of the receiver, have a more expensive receiver than transmit more power. And in some situations that's very much desired. Okay? But in broadcast applications this is perfectly acceptable. Right? So every communication requirement would have a different solution. This is not a solution for all kinds of communication requirements. That's something that I mentioned in the beginning and I'll keep on emphasizing again and again wherever required. Now let's look at how simple the demodulation is. Right? So let's look at the demodulation process. I'll have just time to introduce the demodulator to you and we'll discuss the demodulator in detail next time. The demodulator now requires precisely these three simple components, and this is a demodulation circuit. And what could be simpler than this? Right? You have a diode, you have a suitable value of the resistor here and a suitable value of the capacitor here. Input is your modulated waveform x of t and output is, let's say, z of t, which is, we will soon see, proportional to the message signal mt. Okay. Phase shift of pi by 2. Mt is an arbitrary waveform. There is no concept of a phase shift of an arbitrary waveform. You can talk about delay of an arbitrary waveform. Unless it's a sinusoid, you can't talk about a phase shift. You can talk about a phase shift of a specific frequency component. So please remember, there is no concept of a phase shift. But in many cases, I do not know why you are mentioning that. I think you are mentioning that because you saw a capacitor there, right? No, you have to look at, remember, this is not a linear circuit. Do you see that? Isn't it? You can't just jump to any conclusion here. You have to see how this nonlinear circuit works for us to do what we want it to do. Right? Again, when you look upon it as a differentiator, when you look upon it as a phase shifter, you are looking upon it as a linear circuit, which it is not. Isn't it? There is a nonlinear element sitting there. So unless you understand the operation of the circuit, don't jump to any conclusions. Right? So let's look at the operation of the circuit. Is it clear? So the important point is, you need to understand this operation. The important thing is that if this works, then you don't require any synchronous carrier at the receiver, right? And therefore, as a result, you don't require any expensive carrier recovery circuit. Okay. Now, how will this work? Let me draw a picture. Let's say this is a modulated waveform. This is the envelope of the modulated waveform. Now, because the diode will conduct only when it is forward biased, right? You can think of this action as some kind of a rectification action, but more precisely we will see what is happening. So obviously we only need to look at the positive half cycles of the carrier waves. The negative half cycles we cannot make it forward biased. So we only necessarily make it reverse biased, right? So we only need to understand what is happening during the positive half cycles of the carrier wave. Is that okay? You agree with that?
Only with the positive carrier, sir.
Sorry?
Part. So if I concern only with the positive part, I will be so happy that we got the complete shape of MT, sir. And you said ET follows the shape of MT.
Please let me complete. I have to still explain to you how it is working. The only point I have made so far is that the forward bias to the diode can only come with the positive half cycles of the carrier rate. Is there any debatable point on that? We cannot possibly have a forward bias in the negative half cycle. Right? So it will conduct only, it can conduct only during the positive cycles, positive half of the cycles. Now let us say initially it is let's say initially this capacitor that you have at the output is completely without charge to start with. It doesn't have any charge stored in it, right? So there is no voltage across this. So what will happen during the first positive half cycle of the carrier that this circuit sees, assuming that this resistor is pretty large and this is therefore not very important at this stage, basically what will it do? It will try to charge this capacitor to the peak value of the positive half cycle, right? So that's what will happen. Let me use a different color. So initially output, this was discharge, the voltage was 0, so it will charge like this, right? Assuming that the charging time constant is very small, right? Let's assume that it will follow the envelope, follow this carrier and charge like this, right? And now that the carrier, so what is, when it is charged to this point, what is the voltage here? It is equal to this peak value, and suddenly this input value drops below this peak value. What happens to the diode? It becomes reverse biased. It stops conducting, right? So it will stop conducting. However, what will happen due to the fact that there is a resistance here, there is a discharge phenomenon that will take place. So this voltage value starts to decrease a little bit depending on the time constant of the discharging, right? So let us say it discharges slowly, and this is the way it will discharge, right? Is it clear? And at this time the positive half cycle comes again. At this point the input voltage exceeds the discharge value of the voltage here, and the diode conducts again, right? And again it charges to the peak value, right? And that's the way things will happen, and so as you can see, this charging discharging phenomena under certain conditions would produce an output which follows the envelope, right? Approximately there will be some ripple, right, which you can always remove by a suitable low pass filter. So let me end the discussion here today. We will start again at this point. You please think about it, and we will start again at this point and make sure that all of you fully understand it. Right? Thank you very much.